Hello, I'm Katie Steckles.
And I'm Peter Rowlett. And hi, Katie, what's today's mathematical object?
Today's mathematical object is a space-filling curve, which sounds a lot cooler than it is. It's nothing to do with actual space, but it's to do with, two-dimensional space, like the mathematical space, which of course is better, but not quite as cool as space. But anyway, a space-filling curve. Mathematically, the sort of formal mathematical definition is that it is a map, like a function, that maps a straight line into a two-dimensional space. And obviously there are ways to do that are boring, like just map a straight line in so it goes across the middle. But a space-filling curve is something that fills the whole space, as the name implies. So this sort of function maps it in a slightly complicated way that means that every point in the space is kind of mapped to by part of this curve. And that might sound impossible if you're kind of thinking about a one-dimensional thing that's getting mapped into a two-dimensional thing.
Yeah, I was sort of thinking of sometimes you will talk to me because you're a topologist about a 2D surface embedded in a 3D space and things like the surface of the Earth is a 2D surface, whatever. That makes sense, I think. Yeah. And in knot theory, a knot is a one-dimensional thing embedded in a 2D space. But it feels like if you're filling in the whole thing, you're just making a plane. That's the slightly confusing bit.
Yeah, and that's the confusing thing. But, welcome to infinity, right? Infinity is weird. And also, like, the idea of taking something one-dimensional and creating something two-dimensional shouldn't be too difficult, given that we've already done an episode of this podcast about knitting, right? And this is like the actual, the physical embodiment of creating something two-dimensional out of something one-dimensional. It wiggles a lot, I guess, is the kind of concept you can get from that. And space-filling curves, there's a bunch of different kind of examples of this that you hear about, the kind of famous ones. But they're often defined in a way that's kind of iterative. So you start with a straight line, and then you perform modifications to that straight line, or you add together chunks of it in certain ways, and then you kind of zoom out and do that again. So you get these kind of iterative constructions. So the classic one, and I realise yet again we've given ourselves the challenge of describing a thing on a podcast that is something you really need a picture for. So the photo for this episode is a photograph of a piece of needlework that I've done that has a space-filling Hilbert curve on it, which I have now finished. So it was a labour of months of whenever I could be bothered. But the Hilbert curve is the kind of poster child for space-filling curves. So if you imagine a square grid, and to start off with, it's like a 2x2 square grid. And the Hilbert curve kind of goes from the bottom left to the top left, across to the top right, and down again. And that's the kind of basic unit that you get, this kind of N shape, like an arch, that is the basic unit of that.
Like an upside down U.
Yeah. Kind of, like a hurdle.
Yes.
Right. So
like a croquet.
Like many things.
Yes.
There are many things that are that shape. And there's a kind of implication in the drawing of that shape of a sort of motion, and it's not quite up, across, down, but it's that the first square you've kind of come in from the left, the second square you've gone upwards from the bottom, and the square on the right has a similar sort of thing, except you're coming downwards from the top, and then you go out to the right in the bottom right. And that kind of pattern of movement is the thing that then gets repeated at higher scales. So the next level up from this is in the bottom left corner, there's one of those hurdle shapes pointing in towards the middle. The top left corner has one pointing upwards. The top right corner also has one pointing upwards, and the bottom right corner has one pointing inwards. And it gives you a sort of Y shape that's kind of made out of four of these arches joined together. And I realise it's really hard to imagine, but you kind of keep repeating that again. So you take this Y shape and you put one pointing inwards, two pointing upwards across the top, and one pointing inwards on the other side. Yeah. And then you take that thing and do the same thing with that, and you keep iterating. And I guess if you stare hard enough at the podcast photo and squint, you can sort of see that structure happening throughout what I've got there.
That is literally what I'm doing. Yeah, your Y-shaped thing. It's like it's got a main trunk and then it's got two forks going up either side. But you're trying to describe it in the way that you would actually draw that as a 1D curve. That you start on one side and you kind of go up and round and back down again. Yeah,
it doesn't quite map to going up, going across, coming down, and then going back again, because there's a kind of you also have to join the ends up, so sometimes that happens in slightly different ways depending on how you are relative to the other bits.
Right.
But it is the kind of thing that you can define iteratively in a sort of algorithmic way. So there are ways to sort of program things that will generate these. And I guess this is a version where you're kind of starting from something simple. I guess the basic unit here is a corner, like an L shape. And you sort of do an L shape coming in, you go over the top of the arch with 2 L shapes and then an L shape going out again. And then you just iterate that. And you can imagine that this process has a limit if you continue either continuing to add to your embroidery or just taking the whole thing, scaling it down and putting 4 copies of it together. So you get this sort of fractal-like structure to it. And if you continue that process to the limit, then you get the space-filling curve, and this will then reach every single point of the plane. And in the cross-stitch, it's quite a nice analogy for this, because the cross-stitch has a grid of dots that is, to whatever extent, the minimal, like the Planck length of cross-stitch is the distance between these dots. Yes. And like that, it meets every hole in the grid. And I could do a sort of stretched out version of it that didn't use every single hole on the cross-stitch board, but the fact that it uses everyone, to me, sort of makes this feel more like a space-filling thing. But the kind of mathematical, technical thing is that if you have a space-filling curve, there's a point on that curve that will come arbitrarily close to any point in the 2-dimensional square that you're filling, I guess. Okay. Yeah. And for this cross stitch, I've deliberately used a thread which changes colour along its length, so you can sort of see the gradient. But it actually shows you, it's really nice, you can kind of see which way the curve goes as you follow it along.
I can now. I know that. I sort of wondered why you keep swapping colours and what that meant.
Yeah.
But it was a single
continuous piece of thread. That has the sort of dye that makes it change colour along its length.
And the way that you're stitching this is very authentic to the way that you've described it being made, isn't it? Because you are literally putting a one-dimensional surface up and down this coordinate grid, which is the best.
Yeah, very much. And I mean, you should see the back. It's horrific.
And I can now understand why it's a pain in the neck to actually do it.
Yeah. Yeah. Well, it's very easy to make mistakes. Like I've seen people who've done this and you look at it later and you're like, oh no, you've missed this one stitch and it's changed the whole thing.
Yeah.
But I found this quite a relaxing thing to do because it's got this real beauty to the structure. And I guess the other thing that's nice about this is that kind of inherent paradox that you've got something which is a continuous function, right? It's not doing anything stupid. It's just a map, it's a line that wiggles. But it literally will make a one-dimensional space become a 2-dimensional space. And you end up with this object which has ridiculous properties, right? So this is now a space, an object that is a 2-dimensional shape, right? I can define points on it using 2 dimensions, but I can also define any point on it using 1 coordinate because it's the distance from the start of the line. So that's kind of fun. And it is continuous, but it seems like a paradox that those two things coincide, but this is why they're cool, I guess.
And again, welcome to infinity, yeah. My son was telling me on the walk to school this morning that he's doing a new topic in maths, and they've had 2 lessons so far, and it's angles. And I said, oh, what have you learned? And he said the first lesson was about turns, and the second lesson was about angles. So in the first lesson, they learned about quarter turns and half turns, and then in the second lesson, they learned how many... And then he said how many angles there are in each of those turns. And I said, how many angles are there in a quarter turn then? And he said, I can't remember. So that was our conversation. But this is basically just that, isn't it? You just keep turning a quarter turn each time.
Yeah.
And yet you've built this incredibly sophisticated mathematical object.
Yeah, and I guess you can consider the pattern of lefts and rights that you make. And in fact, there's another way to sort of define these curves in terms of like a replacement thing. So you start with a particular pattern, and then you go back through that list and you say, anytime I've got this, I replace it with this slightly longer string of turns.
Yeah, I wondered that, because some of this, with doing the squinting at it that you were recommending, that I do, yeah, I can sort of see the little Y-shaped thing, but then there's a bigger Y-shaped thing. It's just got more sticking out bits as you go along it, and so there's something like how you build fractals sometimes, is that each edge is replaced.
Yeah, well, it's a thing called an L system, and the L, I think, stands for Lindenmayer, which is the person who originally conceived of this, I guess, and the original use for it was modelling the growth of algae. So Lindenmayer had an L system, which was basically you start off with a unit, which you call something like A, and then you say, whenever you see an A, you replace it with AB, and whenever you see a B, you replace it with A. And this kind of models the processes that happen in an organic system like algae, where sometimes things will reproduce and sometimes things will die out. And if you just take that and kind of repeat that, it will kind of produce an algae-like growth thing. And for things like the Hilbert curve, you can have a thing where you say, okay, I've got my hurdle shape. Whenever I have a left turn, I'll replace it with, I guess in this case, it would be like a left, right, right, left. And then whenever I have a right turn, I'll replace it with this different pattern. And you end up with a way to sort of define this iteratively as a sequence of lefts and rights. And I guess one of the other big examples that I guess people are more used to thinking of in that way is the dragon curve, which I can't remember if we've even mentioned this on. I mean, this is an object in itself that could have its own podcast, but the dragon curve is another example of this kind of sort of single one-dimensional line that gets kind of folded up into a thing. And the way the dragon curve works is you start off with a straight line and you put a fold in it, so it's a right angle, you make an L shape. And then if you imagine doing it with a strip of paper, right? So you start with a flat strip of paper. If you pick up the left-hand end and drop it over onto the right-hand end, you end up with a single fold. If you open that out, you get the 90-degree L shape. But if you didn't open it out, if you just folded it in half and then you pick up the left-hand end again, which is the folded end, stick that onto the far end, if you open that out, you would get a thing that's got 3 folds in it that looks a bit like a saucepan, because it's kind of an L shape with an L shape.
Way. Yeah.
Yeah, so it kind of goes a right turn, then another right turn, then a left turn. And if you continue this, if you iterate this process, you get the dragon curve. And I mean, feel free to Google and look at pictures of the dragon curve. It's incredible. But in the infinite limit of that, you get this wonderful fractal shape, which has got these sort of spirally, dragony looking scales sticking off of it. And it's a fractal. It's got self-similarity. It will, have all of those kinds of properties. But also, it's a space-filling curve, and it tiles the plane, which is what really messes me up looking at a picture of this. It's just the most ridiculous shape. Yeah. It's got all these wiggly edges on it, but then I've seen a picture where someone's just laid 10 of them next to each other. You're like, what? But yeah, so the dragon curve is another one of these. It's also, from one of my favourite facts about the dragon curve is it's in Jurassic Park. So this is a thing I often mention when I'm talking about fractals, that if you, not the film, sadly, that would be incredible. But in the book of Jurassic Park, on the start of each chapter, they have an iteration of the dragon curve getting more complex as the book goes on. And I think because they've got, the Ian Malcolm character that's a chaotician that is in the story.
I never quite feel entirely sure about that, because I read the book when I was a teenager. I've since learned some more maths. I don't know. I mean, is it just, in the film, he just says this is obviously going to go wrong, but not for chaos reasons.
But it's essentially they've kind of they've done the thing that people often do, which is they take the mathematical word chaos and they interpret it to mean the non-mathematical meaning of the word chaos, which is things get complicated. Yes. And in maths, chaos means not things are hard to predict, because in a chaotic system, everything is still completely deterministic, but it means that small changes will have a big impact on the future evolution of the system. So, I mean, a chaotician, which is Ian Malcolm's supposed profession.
Definite job title. Yep.
Not a thing, as far as I'm aware. I mean, you could, if you study chaos, you might call yourself that, but you'd be a dynamicist, right? You'd be an applied mathematician of some kind. But I think his kind of role is to talk about how when you have a system that's as complex as, for example, a theme park full of dinosaurs, any small change will kind of butterfly effect and make unexpected, unpredictable outcomes happen. So,
I guess, or is it the sort of ecosystem thing?
Yeah, I guess.
You've made actually a pretty big change to the ecosystem, because you put some dinosaurs
Well, yeah, I guess in a sort of planetary sense, yeah, you can't you can't just change this and expect it to not have an impact, I guess.
Yeah, and the specific thing is that they've mixed up DNA from dinosaurs and frogs and just assumed it will be like dinosaurs, whereas actually it's a bit more like frogs than they meant it to.
I would be fairly sure that just introducing pure actual dinosaurs would still be a pretty risky, terrifying thing to do, right?
Yes.
They are literally terrible lizards. That's their whole deal.
Yeah, but I don't think his chaos theory predicts that the fences are going to break.
No, or that the one guy is going to try and start selling DNA to some kind of buyer and create a breakdown in the system in order to escape the park. And it was spoilers for Jurassic Park, but
you would need an economist for that. But it's the eggs. It's the fact. It's the fact that they can reproduce.
Yes,
right?
Well, there are a lot of unexpected things. But I guess essentially the role that they've given him is to go, I did tell you this is quite a complicated system. I don't think you can predict how it's going to behave. And like, yeah.
So there's sort of, they muck up the dinosaur park and therefore chaos and therefore the dragon curve. I'm still not quite...
Yeah, it's sort of, I mean, it's, the idea that there's sort of a mathematical instability here that you can model it with somehow. But anyway, the dragon curve exists in Jurassic Park, and I think it's sort of just there to sort of represent complexity and increasing complexity in a system. But it is actually this really incredibly cool object. So, the Hilbert curve, the dragon curve, another famous one. There's a Sierpinski one that is the same Sierpinski triangle person, I imagine, but it is built using a simple thing that you iterate and it gets more complicated, and you end up filling the Sierpinski triangle with this space-filling curve, which is obviously not filling the whole of 2D space because a Sierpinski triangle is a fractal and technically has zero area, and oh my god, but it is, it produces this, in the limit, this fractal.
How is that different then? How does that... Because the Sierpinski, you keep making more and more iterations, or you keep drawing around more and more things, but you aren't getting this property that every point is arbitrarily close to somewhere on this curve, is that?
No, but every point of the Sierpinski triangle is. So it's filling a space, but the space it's filling is no longer R2, I guess. It's filling that particular shape.
Okay.
But I mean, there are a lot of different ways to define this. There are a lot of different ways to define sort of iterative curves. And I guess a lot of them boil down to these kind of L systems. So for the dragon curve, you start with a single unit that you could call, I think I've seen it used F and G as the notation for it. And then you also have defined, so F and G are both move forward in a straight line, plus is turn left and minus is turn right. And if you see an F, you replace it with F plus G. So go forward, turn left and go forward. And if you see a G, you replace it with F minus G, which is go forward, turn right and go forward. And the reason you've got F and G in there and not just one unit of go forward is that they will behave differently in the next iteration, sort of thing. So you can start with that and define the dragon curve. And it's essentially, you've got the list of lefts and rights for the dragon curve. To get the next iteration, you take the list you've got so far, you put a single right turn in the middle, and then you put the list you've got so far backwards at the other side. Or, there are sort of nice ways to kind of imagine that building.
But that's you folding over the bit of paper, isn't it? That's what.
It's the fold in the middle, and everything else is backwards because you've done it the other way around. I'm completely, entirely unsure whether when I say backwards, I just mean in reverse order, or I mean reverse order and flip every left to a right, or both.
Yeah.
But one combination of those things, I'm sure it's someone. And then the other thing that I found when I was looking at L systems, which I really enjoyed, is that if you start with, if you've got a rule called A that is just draw a bit of line, I guess, you start with A, and then the rules are, or B is don't draw a bit of line. So you start with A, you replace any A's with ABA, and you replace any B's with BBB.
Right.
And if you iterate this, you get the middle third Cantor set, which is one of my favourite fractals of all time. Obviously, the least attractive fractal of them all, because it's just a bit of line with some holes in.
Yep.
But you end up with, so your ABA sort of replaces the middle third of the interval.
Yep.
And then on the next run through, the A's at either side get replaced with an interval with the middle missing, and the B in the middle just stays as three B's.
Right. So the B replaced with BBB is just to keep the scale right.
Basically.
It's not sort of one big B, it's now three B's of the same size.
The length of a single unit stays the same, or shrinks, or whatever you want to call it, but you end up with something that increases in complexity at each iteration, and the limit of that is the Cantor set. So you can kind of use it. It very much relates to fractals, and you can use the same kind of language to define fractal shapes as well. Now, obviously, that's not a space filling curve, but these L systems, I think, because a lot of the time when I talk to people about shapes like the Hilbert curve or fractals or whatever, their instinct is to try and create one in a graphics program or code something. And that's kind of what you need to do. That is, you need this sort of algorithmic definition, or just a lot of patience and a needle and thread, it turns out. Yeah.
Right, so the best place to find us both is at finitegroup.co.uk, which is a mathematical community with Discord and monthly live streams and things like that. And the members of the Finite Group were able to listen to us record some episodes from this season of the podcast, if that's the sort of thing you might be interested in.
And of course, as always, both Peter and I blog increasingly occasionally at aperiodical.com. We're still doing stuff there, right? It's still It's a good website. We have mathematical news, book reviews, fun stuff. It's worth a check. And you can also there find more episodes of this podcast.
And if you have any thoughts or suggestions about objects, you can email us objects@aperiodical.com. The music is Funk Game Loop by Kevin MacLeod, licensed under Creative Commons.